Good morning. Today we are continuing with our unit on series. We are looking at properties of series, specifically series with positive terms, the integral test. You'll like the integral test. So we will use the nth term for divergence, work with properties of series, use the integral test to analyze a p-series and approximate the sum of a convergent series. So I know that's a lot going on. So the question is, what is the sum of a convergent series? The answer is truthfully, sometimes we can find it and sometimes we can't. So we don't always know. From the last lesson, you know that with a geometric series, you could find the actual sum of that series, but that's not always the case. Sometimes we can only tell if it converges or diverges. So I have a theorem for us. If the infinite series converges and the limit is equal to 0 as n approaches infinity, okay? If an infinite series diverges, if that limit is not 0. So what it doesn't say that is if the limit is equal to 0, that it must converge. Let me say that again. It doesn't say if the limit equals 0, that the series must converge. It says if it converges, the limit equals 0, but it's not necessarily true the other way around. Think of it as our rectangles are not necessarily squares, but all squares are rectangles. It's that same idea. So use the nth term for divergence. What you're really going to do is look at the limit as each of these approaches infinity. So the limit as, in this case, k approaches infinity of 87. That's 87. It's not 0, so it diverges. The next one is the limit as k approaches infinity of k. Well, that's infinity. Also not 0, it has to diverge. The next one, the limit as k approaches infinity of -1 to the k. Well, that's either +1 or -1. It alternates. +1, -1, +1, -1. It doesn't approach any one value. This does not exist. There is no limit, so therefore I know it diverges. I can prove it diverges. I can't prove that it converges. And finally, letter D here, the limit as k approaches infinity of 2 to the k would be 2 to the infinity, which we know is infinity. That also diverges. So none of those give me a limit of 0. Not that 0 would tell us anything anyway, but because they're non-zero or they don't exist, I know that they diverge. And again, I just want to reiterate this point right here. The theorems above do not state that if a limit as n approaches infinity is equal to 0, that the series converges. Not enough information to prove. A couple properties here about our convergence tests. If we have series A and series B, and they're two convergent series, then the series of those two added together and the series of those two subtracted together will also converge. And you can actually find the values below. So if you can actually find the sum, if you can find that total, then you can add or subtract them accordingly. Constant of multiple series, this would be helpful for us later on, kind of like derivatives and integrals. If C is a non-zero real number, and if the series from 1 to infinity of A of k equals S is a convergent series, then the series, same thing, but with that constant in there, also converges. So moreover, this C that's inside of the series can go to the front of the sigma notation, and it would be multiplied by that final sum. So if the series diverges, then the series with that multiplier also diverges. Example 2, using properties of series. Determine whether each series converges or diverges. If it converges, then we are going to find the sum. For example 1, it might be helpful to put a few of the first terms in there. So this would be 1/4 plus 1/5 plus 1/6 plus 1/7 ... Except for 1/1, 1/2, and 1/3. This is exactly like the harmonic series, and that was in our notes the other day. A harmonic series diverges. So this one also diverges. Okay, so because this is harmonic, it diverges. We don't have to do anything else with that. I will have a way for you to show that or to prove that, again, using either the p-series test or the integral test, and you'll probably like that a little bit better. Letter B. I can actually rewrite this as k equals 1 to infinity of 2 times 1 over k. And that idea of a constant, that 2 can move to the front. K equals 1 to infinity, 1 over k. And now the piece inside, this is the harmonic series. So it diverges. Okay, no problem. Now, the letter C, let's look at these a little bit differently. If I have 1 to the k minus 1 over 2 to the k minus 1, and 1 over k minus 1 to over 3 to the k minus 1, I'm spoke there. Because 1 to any power is still 1, I can actually take that k minus 1 exponent and introduce and take it away as needed. In fact, I can really put any exponent on 1. I know that feels a little bit shaky, but you're allowed to do it. And then I have 1/2 to the k minus 1 and 1/3 to the k minus 1. And so when I look at them like this, they're in that geometric series format. This ratio inside is less than 1. I know it converges. This ratio inside is less than 1. I know that it converges. So I know it converges. And because it's geometric, I can actually find the sum. Remember, we can't find the sum of everything, but we can find the sum of geometric series. So this will be 1 over 1 minus 1/2 plus 1 over 1 minus 1/3. So the first fraction becomes a 2 when we're all done. This is a 1 over 2/3, which is 3/2. So altogether, this is 7 over 2, which is really, really great. Nice. Now, series with positive terms. It means that you don't have any negative signs. And I know that seems kind of obvious that we're stating that right now, but later on we'll have something with alternating terms where they're positive and negative. So right now it's important to establish positive terms. If that series is unbounded, then the series diverges, and that sum diverges, and therefore the series diverges. This is how we show the harmonic series diverges, and that's in your textbook. If that series is bounded, then the series converges, and the series itself converges. That S, I believe, I should say in sequence instead of series. So a theorem, the general convergence test. An infinite series of positive terms converges if and only if its sequence of partial sums is bounded. The sum of such an infinite series will not exceed an upper bound. Basically, we're saying that it has a limit, and that limit exists, but it doesn't go to infinity. An integral test. Suppose f is a function that is continuous, positive, and non-increasing on the interval from 1 to infinity. Also suppose that a sub k equals a function in terms of k for all positive integers k. Then the improper integral diverges. If the improper integral diverges, the series. Then, if the improper integral converges, the series converges. If the improper integral diverges, then the series diverges. So, integral test. If the integral converges, the series converges. If the integral diverges, the series diverges. This is one that we have to memorize. What do we do? Example 3, using the integral test. Determine whether the series shown below converges or diverges. So what we're going to do is set this up as an integral. We're going to go from 1 to infinity. 4 over k squared plus 1. So I've taken that term that's inside this, that term of the sequence, the one that's inside the series, and I've written it as an integral. And this would be, well, I have a k in here, I should probably call it x. This would be a ds problem. So now we're going to get ready to integrate. Here's a 4, can come to the front from 1 to infinity of 1 over x squared plus 1 dx. Now that x squared plus 1 dx, with x squared plus 1 in the denominator, what's the antiderivative of that? It's inverse tangent. So this is 4 inverse tangent of x between 1 and infinity. So this is 4 inverse tangent of infinity minus inverse tangent of 1. So inverse tangent of infinity, the inverse tangent of infinity does actually exist, and that happens at pi over 2. If you think of pi over 2 on your unit circle, pi over 2 is up here. You have the coordinates 1, 0. Tangent is x over y. So that's undefined. So that means we have a very class until it's time to 0. So inverse tangent is going to happen at pi over 2. So this is 4 times pi over 2 minus inverse tangent of 1. That's everybody's favorite tangent value. Happens at pi over 4. And 1/2 minus pi over 4. So now I have 4. And this is pi over 4. So the answer is pi. Now, because we have an answer to the integral that's not infinity, we can say that it converges. By series converges. We cannot say that the sum is pi. It doesn't work that way. We can only say that the series converges, that there is a sum, but we don't know what the sum is. And that's okay. We're not going to ask you for the sum. We just want to know that it converges. So example 4, same idea with the integral test. Determine whether the following series converges or diverges. So this time, we'll set this up as an integral between 1 and infinity, 2x over x squared plus 1. I'll write this as a dx problem. Now this time, it's not inverse tangent, but it's u substitution. So u is x squared plus 1. Du is equal to 2x dx. And lucky for us, everything fits in very, very nicely here. So du over u, integral from 1 to infinity, but remember we have to change the boundaries. So the lower boundary becomes 2, and the upper boundary is still infinity. This is now the natural log of u between 2 and infinity. So natural log of infinity minus the natural log of 2. Natural log of infinity. We used to call it infinity, right? We could say it does not exist because it blows up everywhere. This would actually be diverges. Because we got infinity, I know that my original series diverges. It doesn't have an exact answer. We say diverges. So let's just recap up here. If the improper integral diverges, the series diverges. If the improper integral converges, the series converges. And so that integral test is really, really nice. The harmonic series, I'm just going to take a little side note over here because I never remember the names. But if I look at that harmonic series, that was 1 over k, right? From k equals 1 to infinity. So I can write this as an integral. 1 to infinity, 1 over x dx. What's the antiderivative of 1 over x? It's natural log. So this is natural log of x between 1 and infinity. Natural log of infinity minus the natural log of 1. The natural log of 1 I know is 0. So this is natural log of infinity. I'm left with infinity. It doesn't exist for an integral, right? An integral answer. So we can say that the series diverges. So that's one way that I remember that 1 over k. It is harmonic. It does diverge, but sometimes I need an exact reason why the integral test works. Example 5, using the integral test again. Determine whether the following series converges or diverges. So we're going to write it as an integral to infinity. 1 over x ln of x quantity squared dx. This is really good review for integral stuff. We are going to use u substitution, where u is the natural log of x. Du is equal to 1 over x dx. So when I rewrite this, this becomes du over u quantity squared. If I look at my boundaries, I've got natural log of 2 to natural log of infinity is still infinity. So I'm going to come up here. U to the negative 2, natural log of 2 to infinity. This is du. The antiderivative is u to the negative 1 divided by negative 1 between natural log of 2 and infinity. Negative 1 over u between natural log of 2 and infinity. This becomes -1 over infinity minus a -1 over a natural log of 2. So 1 over infinity, we know is 0. This is 0. Positive, positive. So this becomes 1 over natural log of 2. And because that exists, because there's an answer to the integral problem, we can say that the original series converges. And again, you can't tell me what the sum is. I'm not asking for the sum, but I just want to know, does it converge or diverge? And so it converges. P series, everybody was giggles at this one. The P series is an infinite series in the form is given, where P is a positive real number. So this K on the bottom can change. Yeah, this one's pretty easy. P, if this is greater than 1, we can say that the series converges, but if it's equal to 1 or less than 1, we say that it diverges. So if I go to that 1 over X, well, I guess with 1 over K. That 1 over K series, again, the harmonic one, again, where K equals 1 to infinity. There's an invisible exponent here, which is 1. So in this case, P is equal to 1. So another reason that I know that it diverges. So that's just another way to show. P series are so easy. They're so great. Analyzing to the following converge or diverge. And you're going to think that this is not quite enough work, but I promise you it is. In this problem, you're looking at P. Use the exponent down here that's on the K. P is equal to 3 because P is greater than 1. We say that this converges. And you can be really specific, converges by P series. It's good practice to start because at some point all these rules are going to be given to us at the same time, and we'll have to say converge or diverge, and we'll test what I use. So I'm telling you it's a p-test, but it's good practice to write that in. This problem, example B, is really 1 over k to the 1/2. P is equal to 1/2. Because that's less than 1, this diverges by the p-test. Or P series. We can write it either way, P series or p-test. That's it. All right, my friends, you are going to try the assignment that goes along with 10.3. This is a unit that you don't want to let yourself get behind. I know it's a crazy time of year. I'm going to leave videos for you so that you can catch up when you need to. But you want to make sure that you have 10.1 done before you start 10.2. You want to have 10.2 done before you start 10.3. You want to have 10.3 done before you go to 10.4. This is not a unit that you can learn in one night all at once. It's not going to happen. Trust me on this one. I had a student walk up to me in the library this morning and said, I heard you guys are on unit 10 right now. I remember how tough that was. This was a student from last year. So if you don't want to believe me, that's okay. You believe her. And just unit 10. Unit 10's had it has to be done and loaded. It has to be. Good luck. Remember to reach out if you have any questions for me.